See?
Badge maybe because
You can say a couple.
1, 2, 3, high, high, high. Yeah.
Yeah.
Okay.
And then you can hold on to this.
All
And
right.
then, don't run away with it. I'd like it
I
back.
will. Okay. The next speaker will get it. No.
Here's 2 microphones. We're
I see.
switching.
Okay. I won't run away.
So you have
It's tripartite. It's a triangle.
You're chairing.
Yes, I am.
Good. I'll try to be good with the time.
Yep. I'll give you a 5-minute and then I'll 2 minutes.
Good. And you're also giving us the karaoke. There is a karaoke or something.
Oh yeah.
Oh, okay. Okay.
Yeah.
It's going to be announced.
Is there anything going on? No, I'm just checking the clock.
Am I supposed to start?
No.
Okay.
You're fine.
Okay.
Time my.
I feel like everyone is staring at everyone and someone's supposed to do something.
I think that's someone's speed. So.
But the talk is not on, right?
No.
Okay, good.
There's a clock there in case that helps.
Yeah.
Yeah. All right. Welcome back for the afternoon sessions, everyone. I hope you had a wonderful lunch and enjoyed the fantastic sunshine we had and the conference picture. So just before we get started, there are a few announcements. Victor is bright. So, a few announcements. First, there is an open mic night thing that is happening after the happy hour that we have planned. So there's a happy hour that's happening with snacks and socializing and such after the second set of talks this afternoon. So that's at about 5:15. And then at 7 o'clock, there is an open mic night that one of our AV people in the back, Kevin, can you wave? Wave? All right. Hey. Is orchestrating that's going to be at Mona's, which is a noodle restaurant. And that's at 7, from 7 to 10. Everyone is welcome. No pressure, but if you're enthusiastic about it, feel free to go. Also, keep in mind that there are white paper discussions going on. I realize that it's not necessarily something that will boost your citation count, but it's really important to help garner momentum for saving HSD. So check out the Slack channel and the groups of people who are discussing this during the breaks. All right, so without further ado, we're going to have our first talk. It's a review talk from Tomer Shinar about hard photons in a metal core universe. So,
thank you very much. So I need to do something? Okay, okay. I could talk about the karaoke night as well.
Are you gonna join us?
Of course. You clearly don't know me. All right. Thank you very much. All right, so hi everybody. I'm really enjoying this conference so far, and thanks a lot also to the organizers for organizing this and also for giving me this opportunity. I was asked to give a review on exotic sources of feedback. So I hope I took it in the right direction from someone working from the perspective of someone who works on massive stars and binaries. Much of the things that I'm going to talk about today we heard of already, but I hope that this talk will give you kind of a more concise picture on how these things are connected. And so I thought I would start with a motivation of many of the plots we've already seen, reminding everyone that in the high-redshift universe, we're seeing evidence for very hot and ionizing photons coming from somewhere. We see evidence for peculiar chemical patterns, specifically nitrogen was mentioned quite a lot, and we'll get to this towards the end of my talk. And also bursty star formation, something regulating and governing star formation on smaller scales. So there's all this evidence. This entire conference is dedicated to this. Here we want to talk about some of the more prominent agents of feedback that could be responsible for some of these phenomena. So I'm going to start again reminding what exactly we already heard about very massive stars. So what exactly we mean by very massive stars and Wolf-Rayet stars and their connection. We're going to continue talking about strip stars, the lower mass siblings of Wolf-Rayet stars, and also going to talk about the more speculative chemically homogeneous evolving stars. I'm not going to talk about core collapse supernovae and high mass X-ray binaries, but luckily we had talks on these topics. This is a very rich program, so that's good. So we've already seen this diagram in various forms. How can we study feedback? How can we study what massive stars do to their environment? In low metallicity environments, we want, of course, low metallicity galaxies that have massive stars in them. 1Wiki18 doesn't need an introduction. And it's great, but for the sort of science that I'm going to talk about today, to really understand the results of stellar populations, you typically need spectroscopy, and that's currently very, very tough, except for maybe the brightest stars in this galaxy. These galaxies are really nice, and we already heard of results coming from Sextans A and Leo P and other galaxies in this region. They're closer, but they offer us only limited statistics. I should mention the color here denotes the star formation rate, okay? So these don't really form stars. We only have limited samples of massive stars in these galaxies. And so we're left with the Magellanic Clouds, which I know don't have the lowest metallicities, and so some people don't care that much about them, but really it's they're gifts of nature. We have to throw whatever we can and really make sure we understand these populations at a fifth and half solar metallicities. So before we start talking about the agents, let's be reminded that massive stars typically are born in couples, and in these couples they interact. Okay, the majority of massive stars will interact with companions. We also heard about this earlier. So far we knew this from studies in the Large Magellanic Cloud and in the Milky Way. Now we also know this in the SMC. So this plot was shown several times. I'm not going to talk about correlation with metallicity. That's beyond the topic of what I want to talk about. But suffice it to say that we see at SMC metallicity a lot of binaries. Okay, so we know that they're very common at least at SMC metallicity and probably at lower metallicities too. So the Bloom survey was mentioned several times, and I had to also mention it because that takes most of my time. and we work on this heavily. The Bloom survey is a multi-epoch spectroscopic survey where we acquired 25 epochs of observations over the course of 2 years for about 1,000 massive stars in the SMC. We have a lot of science goals, like getting not only binary fractions, but complete orbital parameters, orbital parameter distributions. We want to constrain the IMF empirically, find black holes. There's a lot of physics we want to do here. I think that many people in the audience would care about the outputs coming from this survey. But now I just wanted to kind of mention it because later on I'll refer to a few results from it. And just to give you a sneak peek, right now we're at the stage of really getting all those orbital parameters out, like period distributions, eccentricity distributions for the different samples. This is muchly work led by my students, Zahava, Roy, and Tom. Okay, so talking about our first agents, we heard quite a lot about them. Wolf-Rayet stars. So per definition, Wolf-Rayet stars are hot and windy stars. Okay, it's actually a spectral type. You want your spectrum to look something like this. You want to see a spectrum which is dominated by broad, strong emission lines coming from winds. By nature of their definition, they're important for feedback, right? Because they're hot, meaning they're ionizing, and they're windy, meaning they have substantial mechanical energies. So how do we get them in nature? You want the star to drive a strong wind. Why do stars drive strong winds? That happens when they approach the Eddington limit. Okay, we heard about this already. Their luminosity to mass ratios become extreme. And nature does this in two main ways. Either the luminosities are driven to very high values, and this happens to about 10% of the known Wolf-Rayet population. These are the very massive stars that we heard also in Yorick's talk about. Stars with masses in excess of 100 solar masses or so, they're going to have Wolf-Rayet-like spectra. And we're going to spectroscopically see them as Wolf-Rayet stars. And only if you have a very fine eye, maybe you'll find some hints that they're very massive stars. The other flavor of Wolf-Rayet stars are these classical Wolf-Rayet stars, which is what we typically think of when we talk about Wolf-Rayet stars, which are these evolved helium-burning stars typically that sit here. That's about 90% of the population. And we get there by stripping the progenitor masses somehow. And we're left with a much lower mass score. That's why they're driven to the Eddington limit, because they lost a lot of mass. So why do we care about them? Let's look a little bit about what they do in terms of feedback. So what I'm plotting here, I took the LMC population of the majority of Wolf-Rayet stars that were analyzed. That's WN stars in this case. What you see here are the number of hydrogen ionizing photons as a function of the spectral type of the Wolf-Rayet star, compared to a typical output of a 60 solar mass O star, which is kind of the highest mass O star that you could possibly have. And all these dots here, you see there is a lot of scattered. This is a logarithmic scale. So there are a few stars here that really dominate over the entire thing. Of course, O stars are much more numerous, so it's hard to tell which ones would dominate. That would depend on the environment. But Wolf-Rayet stars are very important contributors to this total output. But if I look now at helium-2 ionization, and I look at what a 60 solar mass O star does, at least the type of O stars that we know, and again, this is a logarithmic scale, you see that they're completely negligible compared to Wolf-Rayet stars. And among the Wolf-Rayet stars, it's the earlier ones that dominate again by orders of magnitudes. So this is a case where really a few individuals can completely shape the properties of the entire population in terms of ionizing output. And the same goes for a mechanical luminosity. Maybe not as extreme as helium-2 ionization, but mechanical luminosity is easily exceeded by Wolf-Rayet stars simply by nature of their strong winds. So we care about these stars, obviously. Okay, so there are two main ways I want to discuss. The first is we care about how massive stars actually get, and I'm not going to solve it in this talk. I have exactly one slide dedicated for this. And the second is how do we form those classical Wolf-Rayet stars? So this actually Paul already alluded to in his talk, or actually talked about those very massive stars. How do we know how massive stars actually get? It's hard to answer from first principles, right? I mean, I'm sure many people here have different opinions. It could be dependent on metallicity. One thing we can do is to look at nature and find the most massive stars we can. And the current record-breaking stars are situated in the core of the Tarantula Nebula in R136 in the Large Magellanic Cloud. And this region actually has a funny history. In the past, people thought that this was one big star that weighs 2,000 solar masses. Then it was resolved. Eventually, Paul Crowther managed to resolve it with Hubble Space Telescope and identify these components, A1, A2, that were estimated to weigh between 200 and 300 solar masses. And the question remained, however, is this the end? Were they now fully resolved? Do we have stars that weigh as much as 300 solar masses? A few years ago, we tried to probe whether there are any companions to these stars on close orbits of days to years with spectroscopy, and we couldn't find any evidence for this, so that was good. But this year, for the first time, a binary was resolved outside our galaxy with the Gravity Plus collaboration, which is really a fantastic scientific achievement. I mean, it's really amazing. They found for the most massive star a nearby companion. This companion is only 100 solar mass star, 100 solar masses, and it turns out that the impact on the mass estimate of this primary isn't that severe. So it goes down from about 270 to about 240 with large uncertainties. But still, it shows you a very interesting tale of how we keep finding those stars. So far, we still have stars that seem to exceed 200 solar masses right in our neighborhood. So now classical Wolf-Rayet stars, right? The bulk of the population of Wolf-Rayet stars, how do we form them? One route is simply for the star to somehow manage to get rid of its outer layers by virtue of mass loss or potentially eruptions, okay? And if stars are massive enough, they can actually, we think that they can do that. That's probably metallicity dependent. There are a lot of uncertainties here, but probably very massive stars at a certain point can get rid of their outer layers and become classical Wolf-Rayet stars. On the other hand, we know that the majority of massive stars are in binaries. Binary companions are very effective in removing outer layers. So we have another efficient route of stripping our stars, and that's the so-called binary channel. Okay, we want to know which of these channels actually governs or dominates the populations, maybe dependent on the environment. One of the ways to constrain this empirically is to look at the binary fractions, right? Do we see all Wolf-Rayet stars in binaries, or many of them are single? What's going on? So it turns out that no matter where we look with spectroscopy and interferometry, the binary fractions of Wolf-Rayet stars appear to be of the order of 40 to 50%. Or in other words, roughly half the Wolf-Rayet stars don't have any evidence for companions around them. And that's a problem, because if we look at the Wolf-Rayet population, for example, in the Large Magellanic Cloud, so you're seeing it here on the Hertzsprung-Russell diagram, and you're comparing them to state-of-the-art single-star evolution tracks. These are Geneva evolution tracks, which account for rotation. You'll have a very hard time reproducing these Wolf-Rayet stars. Okay, the tracks simply don't want to get here. And so you can say maybe they're all binaries, but we're not seeing those companions, okay? So that's our problem. And other tracks might do better here, but this is almost always a problem that we encounter. So what's the way out? Either our single-star evolution tracks are not well calibrated. That, for example, could be resolved with enhanced mixing, which I'll talk about in a few slides, or enhanced mass loss rates, right? If those tracks would lose magically a lot more mass, we would be able to maybe reproduce this population. Or all these apparently single stars, let's be reminded, many of them might have had companions in the past. Maybe they're the product of some non-trivial binary evolution that is not standardly predicted by our models. For example, supernovae ejections, mergers. None of this is trivial, but we need to keep these options in mind. One thing is for sure, as we look at the Wolf-Rayet count as a function of metallicity, and here I want you to look at the red line, which is normalized by star formation rate, we see a very sharp drop in the Wolf-Rayet formation efficiency. So as we go to 1/18, even though there are a few tens of Wolf-Rayet stars estimated there, if you normalize the star formation rate, we hardly get any Wolf-Rayet stars. So why is it that we hardly see Wolf-Rayet stars at low metallicity if we have all those binaries stripping our stars? The answer is, we think, it lies in the fact that the Wolf-Rayet phenomenon itself is metallicity dependent. As we go to lower and lower metallicities, the stripped products cannot launch powerful winds. We don't see them as Wolf-Rayet stars. They would look like something else. And we see this pretty clearly empirically as we look at the Wolf-Rayet populations in the Milky Way, Large and Small Magellanic Clouds. We see this kind of trend. Yes, there is a problem of statistics, but we work with what we can, and we see a clear trend, and also this is what we'd expect from theory. So instead of Wolf-Rayet stars, we expect to see something else here, which takes more and more space as we go to lower metallicities, and these are our strip stars. So strip stars are the weak-winded Wolf-Rayet stars. They're lower luminosity siblings. And they're also very efficient in ionizing photons, right? They can be equally hot to Wolf-Rayet stars, and they don't even have these winds to absorb their radiation. So they're very efficient in this sense. The question is, are they more important, less important than Wolf-Rayet stars? And obviously that's going to depend on the metallicity. So we've already heard of these stars in Beryl's talk, and these are some estimates for their numbers for different metallicities. Basically, you can take these models, or you can do some form of estimates. You could estimate that in our Milky Way galaxy, something like 10,000 to 100,000 strip stars exist in our Milky Way. The interesting thing is that we've never unambiguously detected a single one. Okay, it's a much more common population than Wolf-Rayet stars, but we've never actually detected them, which is interesting. But it's also pretty clear that they're very hard to detect. We have better prospects in the Magellanic Clouds, which has much lower reddening. And indeed, a few years ago, for the first time, Maria Draut and Ilva Gutberg managed to identify the first sample of such lower mass stripped stars, a few tens of them. This year, Ludwig et al. Published a new list of about 1,000 candidates for stripped stars in the Magellanic Clouds, of which roughly 100 are considered good candidates. The others are potentially contaminants. So these numbers are growing, and it's impressive. The question is, are we potentially over-predicting stripped stars? Because they're predicted to be very abundant in models, but we're not actually observing these numbers. So this year, Blomberg et al. Actually did a very nice work where they took a synthetic population of stripped stars. They forward modeled them through all the biases that we suffer from. And it turns out that indeed, if you account for all the biases, you detect less than 10% of the population. So the numbers that we're observing could be consistent. But we're still in a low statistics regime where it's hard to argue whether or not we're actually consistent. But another thing that we need to keep in mind is that, especially at low metallicity, we're not sure how the bulk of the stripped star population looks like, and I think this is of wide interest to this public as well. For example, Klensky et al., they showed in their paper that this is a model, I forget, I think for a 30 solar mass star that gets stripped. In solar metallicity, you see that it goes all the way to these hot effective temperatures. At SMC-like metallicity, you get this cool product. You get something called a partially stripped star. The star doesn't really get stripped of all its hydrogen, and it remains kind of hydrogen-rich and puffy. And the question is, what happens is, as we go to even lower and lower metallicities, do stripped stars even become hot? That's, I don't think, something we actually know. We can speculate on with models, but we don't know. So it's something important to keep in mind. Okay, so that's what I said. Last bit, okay, still have some time. I will talk about chemically homogeneous evolving stars as our final agent. So these kinds of stars were speculated already in the 80s to exist. People like Menet and Medel, the developers of the Geneva Code, they noticed that as they crank up rotation or other forms of mixing, instead of the star evolving to the right here and becoming some kind of a red supergiant, the stars would evolve homogeneously. So they remain compact and very hot throughout their lives, and therefore emit a lot of ionizing photons, and therefore it's relevant for this conference. So does this happen? Do some stars actually evolve like this? This could be very important, because then their entire main sequence lifetime, they're going to be hot and ionizing. But to get these kind of models going, standardly, you would need rotation velocities of the order of 500 kilometers per second. When we look at observed distributions of rotations, and I'm very biased, I'm taking here the Bloom survey, but there are many other surveys that show this, we hardly see any stars that rotate as fast. Maybe there are the occasional few, and even then we don't see clear evidence for homogeneous evolution. So is this something that happens in nature? There are a few claims. Maybe I will highlight this one. This is a recent work where the authors argued that the properties of 1 Zwicky 18, the integrated properties of this galaxy, are consistent with models that assume that about 10% of the stars evolve homogeneously. And that's a nice claim, and it's intriguing, but my personal opinion, I don't think it's sufficient evidence, because there could be other models that match this. So to really know that we see chemically homogeneous evolving stars, to me, proof would be seeing a star that lies to the left, a main sequence star, that lies to the left of the zero-age main sequence. And if anyone finds such a star, please let me know or publish this in Nature. Okay, this would be an important find. So far, I've not seen such an object. But maybe I'm not a big believer of this chemically homogeneous evolution, or at least not of proof so far found for it. But I do think that there is very strong evidence that stars are more mixed than what we previously thought. And to show you again an example from the Bloom survey. This is taken from Danny Lennon's work that was published this year. What you're seeing here are rotation rates of stars in the Bloom survey. I won't enter now the details of single stars and binaries and all of that. Where you see red is where you have rapidly rotating stars, and yellow means slowly rotating. And the authors identified this region where there's a sharp drop in the rotation velocities. Okay, and this is thought to correspond to the terminal age main sequence, where there's suddenly a transition where the stars should enter the Hellstrom gap or something. And if you look at the tracks in the background, which are kind of standard tracks with standard overshooting that we typically assume, you see that there is a gap here. And this gap, to reconcile for it, you need to really increase substantially the overshooting parameter. So that means that the cores are bigger than we previously thought. It really impacts the forward evolution of these stars significantly. And now we also have the ability to look at the binary properties of these stars to the left and to the right of this region. For example, we see a very clear difference in the binary fraction properties, the median period, and other things that I won't talk too much about. So we think that overshooting is likely underestimated. And to show you one last piece of evidence that I think could be interesting for this public, for why we think that mixing could be underestimated, this is from a paper that Pablo Marchant and I literally submitted today. Pablo should have submitted it today, so I hope he did. Otherwise, that's a lie. Where we looked at nitrogen, our favorite element in this conference. And we asked ourselves, well, we talked about nitrogen, and we realized that nitrogen enhancement, as Yorick already mentioned, is very common in massive stars. CNO processed material, we see this very commonly. But we see it really commonly, a bit disturbingly commonly. So this is what you're seeing here is we're plotting the fraction of nitrogen-enriched stars as a function of luminosity or mass, if you will, in the Tarantula Nebula. We have a sample of 122 stars, and we're plotting the fraction of nitrogen-enriched stars. And nitrogen-enriched here means a factor of 10 over baseline. Okay, so it's a very significant nitrogen enrichment. And what you're seeing is that above 60 to 80 solar masses or so, and definitely above 100, close to 100%, that's the gray curve here, okay, with its confidence intervals. Close to 100% of the stars are nitrogen enriched. Basically, you don't see any stars that are not nitrogen enriched. That goes in line with what Yorick Vink said earlier, that very massive stars naturally produce a nitrogen. And we see this empirically. But the problem is that it's not that easy to get from models. Models you somehow need to expose this nitrogen. You need time. Even for very massive stars, you still need time to expose this nitrogen. And Yorick showed an example for a 300 solar mass star. But here we're talking about 100 or even less than that. If you compare this numerically with models, and you change different assumptions on mass loss rates and star formation histories and stuff like that, it's very difficult to reproduce this feature. The only parameter that helped us reproduce this is, again, this overshooting parameter. Yeah, with all these different models, no matter what we do, it favors very high overshooting values. Problem is that if we take these overshooting values, the stars all evolve homogeneously, and this contradicts their position on the Hellstrom-Russell diagram. So we speculate that there is some kind of mixing process, maybe related to the star formation process itself, which is, I'm pointing at you, Piyush, maybe related to the way that the stars are forming, that stops operating at a certain point, but really mixes the stars and also creates this very strong nitrogen enrichment that we currently are not reproducing. Okay, yeah, I have 2 more minutes, but I'm with my summary slide, so I have some time to go over it very quickly. We talked about these 4 objects, right? Very massive stars. All I want to say about them is that they exist. We know that, yeah, I'm very empirical, so I only believe what we see, and we see those guys. We talked about Wolf-Rayet stars. This is maybe a bit of a vague claim. I argued here that likely dominate feedback at metallicity is larger than a 10th solar. What I actually mean here is that well, it depends on what kind of feedback you're talking about. I guess I'm comparing them here with stripped stars. I think they're equally or even more important. Of course, it depends also on the delay times and what exactly you care about. But we have the big issue that at least in the clouds and also in the Milky Way, these populations are not well reproduced by current models. And if we cannot reproduce these populations, your models in the high redshift universe are equally or even more shaky, right? So we need to be wary of this. And we saw that as we go to lower metallicities, there is a very low formation efficiency for these stars. Instead, we're being taken over by these stripped stars that span a larger mass range as we go to lower metallicities. That's why they are more likely to dominate feedback at lower metallicities. We only just potentially detected the tip of the iceberg, but I think a very important question we need to be critical of is, are they really hot as we go to lower and lower metallicities, or maybe they remain cool throughout their lives? And finally, homogeneous stars, there might be hints for their existence, but no direct observations so far. But there are, I think there is very strong evidence for enhanced mixing and enhanced nitrogen enrichment. That should be 60 solar masses here for masses above 60 solar masses or so. So with this I end, and I'm happy to take questions.
So the new figure with Fabio, could you explain why you're cropping this gray bar?
Here.
Yeah.
This one? Yeah.
How did you get this?
Okay, we looked at a sample of 122 massive stars in the Tarantula Nebula that were well analyzed, which have measured nitrogen abundances. And it's a binary question. We ask ourselves, is this star nitrogen enriched or not? And we define it by a factor 10 enrichment. If we see a factor 10 enrichment compared to the baseline value, we call it nitrogen enriched. And we ask ourselves, what's the fraction of enriched stars as a function of luminosity? And that's what we see here. Okay?
Baseline.
What's the baseline? You want the number.
Well, and like nitrogen relative to what?
No, nitrogen relative to nitrogen. So we have one. No, it's
Yes.
there is the LMC. There is the LMC kind of, right? We have the solar abundances. We have LMC abundances. So we know what nitrogen should be in the LMC. There is well, okay, you could debate this, but there are nebular diagnostics, there are B-type diagnostics, there are okay, fair. So but the important thing is that no, it's a good point. I think it's a fair point. I mean, but I cannot tell you the number, but there is a certain baseline based on literature. That's the baseline that, you know, when we calculate models, we plug in this abundance. If it's 10 times that, then we call it nitrogen enriched. Okay.
Thanks for the nice talk. So I was wondering, with the last point you mentioned on some additional mixing mechanism needed, if these stars are still accreting, could that provide some more mixing, or is that's not very good?
Yeah, so I don't think they're still accreting, because we would probably see this in different ways. Most of them don't have like signs of accretion around them or something like this. They're embedded in the Tarantula Nebula, but the Tarantula Nebula is largely, you know, spread. But I think if earlier on in their lives, as you said, maybe they got to their main sequence, started producing CNO enriched material, and they're still accreting, maybe this helps pump out this nitrogen outwards.
Is there a way to like model this? Like,
I don't know.
Yeah, thanks for a great overview. I have a question also about this figure. The peak at like 60, where it goes almost up to 100 and then drops again, do you think that's physical? And if so, do you know why?
There are some biases here, because it's 122 stars, so there are some issues here with the binning and how exactly you would bin it. I doubt this is some real feature. That's why I'm saying 60 to 80. Depends how you bin it. You would get this earlier or later. But basically, there are still a few stars here which are not nitrogen enriched. And then suddenly you don't see them anymore. Yeah.
Okay, and while Daniel's asking your question, Ivan, would you please come up for your talk?
I'm just going to ask, so okay, nitrogen rich, great. What about that nitrogen actually getting back into the ISM I mean, if it's well mixed, it's throughout the star, right? So are we getting the levels of nitrogen out, do you think,
Right.
from these models?
So it's not something we estimated, but I would say so because these kind of stars, at least in the tarantula, in this metallicity, they have very strong winds. So one could compute the yields and all of that, but my impression is yes, they have very massive star kind of like winds, and they're going to lose them. Yeah.
All right, let's thank our speakers.
That works. All right, can I be heard? Okay. So my name is Ivan Altunin. I'm a PhD student at the University of Nevada, Reno. My advisor is Rich Plotkin, and we recently just posted this work on arXiv, and we should hopefully have it published in the next couple of months as well. So to kind of start off with, we've had a lot of great discussions over the last couple of days on the similarities across cosmic time and also the dissimilarities, importantly, between dwarf galaxies. But one similarity that does stand out is that regardless of where you look, across all epochs, we see dwarf galaxies or nebulae that are highly ionized, and it is not very evident what are producing the ionizing photons that are producing these regions that we see at low metallicities. Of particular interest for my work are helium-3 regions, which are regions of doubly ionized helium, requiring some source of photons above 54.4 electron volts. And of course, we can't see into these regions directly, but instead we infer their presence through the recombination lines that we see. I'm particularly interested in the 4686 angstrom line, which is the result of ionized helium recombining with an electron and that electron cascading from the 4th to the 3rd energy level. We've heard a lot about the potential ionizing sources for these regions, including the population 3 stars, the very hot or very massive stars, the Wolf-Rayet stars, the strip stars, the binary, all these different sources. Here the key parameter is temperature. The hotter your star is, the more ionizing photons you're going to produce. In the high metallicity environments, Wolf-Rayet stars are kind of the accepted source for these ionized regions. However, as we just learned and have been talking about all week, Wolf-Rayet stars become uncommon at low metallicities. Luckily, binary interaction comes to the rescue and allows Wolf-Rayet-like stars to form at in these low metallicity environments. However, with the caveat that their spectral features are often absent or obscure. So a natural question is, how do we test whether these are the emitters of these ionizing photons? And I don't have a good answer to that. A lot of people have been discussing their own work, how they do this. But another way of approaching this is by starting out by ruling out other types of sources. A potential type of source is X-ray binary stars, which thanks to Antara, I don't have to explain what they are. But there are also additional products of binary evolution. They're well-known emitters of high-energy ionizing photons, and crucially, they have been shown theoretically and empirically to be found common at low metallicities. So we test the X-ray binary hypothesis as ionizers of helium. We had a sample of 23 galaxies, some of which are shown here, but we had 23 total. These galaxies were taken as a subset of the Shirazing-Brinkman sample, which, if you're unfamiliar, they took the STSS data, they took a subset that had helium-2 emission present, a subset of that were star forming, and yet another subset of those that had Wolf-Rayet spectral features missing. And then my advisor submitted requests to get Chandra X-ray observations for the most metal poor of these galaxies, and then we also took whatever archival data was available as well. This is our sample on a BPT diagram with several different diagnostics. As you can see, one AGN kind of snuck into our sample, and that'll become important a little later. Okay, so as has been the common theme throughout this talk and this conference, we can't see into these regions directly, and so we have to get creative with how we're inferring the EUV the EUV photons and the things that are producing them. This is kind of the outline of how we do this. First, we characterize the EUV from our optical spectra that's producing the ionized helium that's producing the helium-2 line that we see. Then we characterize the host environment. We look at metallicity, star formation rate, and dust. We estimate the EUV that's being produced by creating objects in our sample, and then compare and see if they're able to describe the deficit. Okay, so that first step. So what we see as astronomers is the spectra that we get from Sloan Digital Sky Survey, and we see this recombination line. However, this does not tell us anything about this does not tell us all we need to know about the EUV continuum, because it is the result of an electron recombining with ionized hydrogen, and then by chance that electron cascading from the fourth to the third energy level. So we need to take into account that that there's a certain rate at which recombination happens, and there's a certain probability at which this electron cascades to the appropriate energy levels. Using theoretically tableized values, we can find that for every 4686 angstrom photon that we see, there was about 5 EUV photons that were emitted. So that's our optical data. This is our X-ray data. Of the 23 galaxies, 6 of them had X-ray detections. Some had more than one X-ray detection. The X-ray detections are shown in red, and the yellow circles are the STSS fiber. As you can see, our pesky AGN is there in the bottom right-hand corner. Again, will become important later. As mentioned, we performed some additional SPS modeling using Prospector to fit STSS spectra and photometry simultaneously to get constraints on the star formation rate, metallicity, and dust as well. The reason we care about this is because, as mentioned in previous talks, there's a relationship between X-ray luminosity and host galaxy properties. When we see our sample overlaid with these relations, we can see that for the points that had X-ray detections were, well, first off, as mentioned, this relationship is quite scattery and noisy to begin with at these low metallicities. But for the points that had X-ray detections, they sit above this relation. And I forgot to mention this before, but for points that did not have X-ray detections, we provide upper limits. The astute amongst you would have already noticed that I provided those green or blue triangles on there that show the required X-ray luminosity to explain the helium-2 line, and you might be wondering how we got those values. To do this, we exploit probably one of the greatest things about X-ray binaries, which is they emit across a wide variety of wavelengths, all the way from the ultraviolet to the X-ray. Unfortunately, we do not know anything about these accreting sources a priori, and depending on the state that they're in, this can affect the emission that we see. So if they're accretion dominated, we see a multi-temperature, their emission can be modeled as thermal emission and can be modeled as a multi-temperature disk black body. If they're corona dominated, then instead their emission is modeled as non-thermal and is instead dominated by inverse Compton scattering and modeled by a non-thermal power law. So we fit, because we don't know anything about our sources beforehand, we fit both models. These are kind of the two extremes. Of course, X-ray binaries can sit anywhere in between, but we fit both models to all of our sources. And here's our main takeaway. On the left, you have the result from the power law fitting. On the right, from the multi-temperature black body fitting. And on the x-axis, we have the number of UV photons that are being emitted by our accreting objects. On the y-axis is the number of UV photons that are creating the ionized helium that's creating the 4686 angstrom line that we see. As you can see, the vast majority of our sample falls below the one-to-one comparison line, with the exception of maybe 3 sources, which are labeled on there. One of those sources is that AGN, which snuck into our sample, which is a call out to those who are working on it to increase our, or to improve our BPT type line ratio diagnostics. But then also, it's even though it did sneak into our sample, it's kind of a happy accident because it helped test our methodology. The other 2 galaxies on there, when you dig into the literature, their helium-2 emission is associated with either a hypernova event or many hundreds or thousands of supernova events. So in conclusion, we've kind of, in our sample, we do not believe that X-ray binaries are the dominant source of ionizing radiation, and they're not a single source of ionizing radiation. I emphasize that they're not a single source because as part of this work, there was a large literature review done on all the different types of ionizers, and in some cases, Wolf-Rayet stars can provide the ionizing photons, in some cases supernova, in some cases X-ray binaries. And so I think that this might be an indication that it's time to abandon the single source model, and perhaps all these sources are working together in concert to provide these ionizing photons all together. Thank you.
All right, we've still got some ample time for questions, so have at it.
I'm just curious, in the spectrum you showed, like it looked like there was a bump for Wolf-Rayet features. You considered what type of Wolf-Rayet population you would need to produce the helium-2?
Are you talking about this spectra? No, so all the spectra that we had been classified by Strauss and Brinkman as not having Wolf-Rayet features. So we kind of took that at face value, but that's something that's worth revisiting.
I was wondering if you could say something about, I guess when I think about X-rays from things that have helium-2 emission, I don't always assume that the X-rays can always get out on some of these gas-rich sources. And so, like, at most it would provide like a lower limit when we detect the X-rays because they can be quite sensitive to the gas and dust there. Did you guys think, like, did that go into your argument?
Yeah, so not included in this talk, but in the paper we have a lengthy discussion on dust, and part of our SPS modeling was recovering dust. And we find that unsurprisingly, these galaxies don't have a lot of dust. And so we don't think that's happy to talk about it more, but we don't think that is an explanation for why these X-ray sources are too dim to explain helium-2.
Else? I have a question.
Yeah.
So you list one of the galaxies, and there is NGC 5471, but that's actually a giant extragalactic region.
Yeah.
So,
yeah, I don't remember which one it actually is, but as you can see, some of these galaxies are either by galaxies we mean they're the Sloan fibers that we have access to, and so it could be a region within a bigger galaxy, or as you can see, it might be one of the bottom ones, maybe a region overlaid on top of another galaxy that got a little confused with the identification. Yeah. Thank you.
Yes.
I might have to miss something, but X-ray binaries in general, you show a plot where you show two classical states, usually associated with low-mass binaries, but then you also show microquasars like the Felix plot, high-mass binary. So how are you considering those both sources that are really intrinsic different, like one shows outbursts, the other one is kind of persistent emissions? Like how are you distinguishing those X-ray binaries?
Yeah, so we're assuming these are all, if they were sources, were X-ray binaries, we're assuming they're high mass X-ray binaries, just as an assumption for our modeling.
All right, just one more, just a clarification. Were you treating these as being ionized or potentially ionized as a single X-ray binary, or was it a population of X-ray binaries?
We don't distinguish between the two. It could be one or the other, either one big X-ray binary or a population. We're just looking at the intrinsic X-ray luminosity, seeing if that's enough to explain it. But we didn't actually go and do the work to identify what type of sources these are. Yeah.
Constantinos, could you come up, and then while you come up, let's thank our speaker again.
Yeah, perfect, thanks. Well, hello everyone. I'm Kostas. Okay, we started from a slide further down. Let me go back to my first slide. So, I'm Kostas Kouroumpadzakis from the Astronomical Institute of the Czech Academy of Sciences. And since this is the first session, after lunch, I thought I could offer you some refreshment in the form of a fruit salad of star-forming galaxies. And that's because I will be discussing about green peas, blueberries, and maybe even like a bit of raspberry galaxies. Anyway, so what are those sources? So we know green peas since 2009. These are low mass, dwarf, compact galaxies with low metallicities, relatively nearby at races about 0.3, and their distinctive green color is due to enhanced O3 emission falling into the visible light. Blueberry galaxies are even lower stellar mass sources, even more compact, highly star-forming again with lower metallicities and more nearby. Then distinctive blue color is due to enhanced star formation. So why should one study those sources? First of all, we've seen some remarkable observations with the advent of JWST. You all know that. So for instance, we managed to see galaxies at races of 7, 8, and even further on. Here I'm just showing some observations and comparisons of these dwarf high-jet galaxies. This should be it. And these three sources at the bottom are at races at about 7 and 8, and at the top is a green pea galaxy from the nearby galaxy, from the nearby universe. So we've seen some remarkable similarities, as you can see in the spectroscopic emission. The similarities also stand with respect to their morphological properties. For instance, the half-light radii as observed in the UV emission falls well within the distribution of green pea galaxies of those high-redshift sources. So take a look at these papers if you want to look more comparisons about green peas or these local analogs of high-Z sources. But then, since we can directly observe this high-Z universe galaxies, then why should we care about local analogs? Well, there is no equivalent of JWST in the X-rays or even in the infrared, I would say, or the radio emission. So if we want to have the full picture of how these sources emit and evolve, then we need to rely on their local analogs. To that respect, we wanted to create, to find a sample of blueberry galaxies that are more nearby and more accessible to study. And we went to look in the Cecati catalog, and we managed to identify 48 blueberry sources up to 200 megaparsec. We found the most nearby one at a distance of about 20 megaparsec, pretty close to the Svitley 18 galaxy that we all really love. And then, of course, we managed to do some analysis. So here I'm showing the color optical diagram of those sources. And let me explain. So with blue and purple are the blueberry galaxies from Young and our work. With red are the extreme emission line galaxies from Izotov 2011, and green are the green peas, and with gray as in the background are the normal population of galaxies from the Cecati catalog and SDSS. So what we take away from this comparison, first of all, is that we see that there is a continuum population of extreme emission light galaxies, and green peas or blueberries belong in this population. However, these are the intrinsic K-corrected colors. We see that green peas and blueberries are different populations. So to that extent, we cannot say that blueberries are just simply local green peas. Blueberries are the bluest among of those extreme emission line galaxies. We went on to examine also their star formation rates and stellar masses. What we see here is the main sequence, as it's called, of the star-forming galaxies, mainly described from these fits. However, we see that the blueberry sources are the lowest mass of those type of galaxies. And of course, they have the highest specific star formation rates in comparison to both the green peas and the larger population of extreme emission line galaxies, and of course, the normal star-forming galaxies. These comparisons continued with spectroscopic properties. So here I'm showing the same coloring. Blueberries are with purple and blue, green peas with green, and with the red are the extreme emission line galaxies from Izotov 2011. So in all these comparisons regarding their specific star formation rate, the star formation rate over the stellar mass of the sources, the Balmer equivalent widths, the oxygen 3 equivalent width, or even the O3-2 ratio, which is a tracer of the ionizing conditions or the effective temperature of the gas within the systems. We see that blueberry galaxies are at the extreme end of these comparisons. They are stronger, more active compared even to green peas on average, which are already more active on average with a population of extreme emission line galaxies, which is by far more active, of course, with a normal population of star-forming galaxies of the universe. Moving on, I'm not showing here the mass metallicity relation of those sources, but just show for now the comparison between metallicity and extinction for those galaxies. We see, first of all, that the extreme emission line galaxies and the green peas, although there is quite a bit of scatter, tend to follow the relation. However, blueberry galaxies seem to have higher extinction with respect to their very low metallicities. And this means that they have a little bit of dust, and that brings me to the next slide. So since there is dust, these sources also emit in the infrared. So here I'm showing the mid-infrared WISE color diagram comparison. I'm also keeping the same coloring of the points. Blueberry galaxies not only emit in the infrared, but also are among the reddest infrared sources of the local universe. They're as red as some of the Lyrics and Julics, which are far more massive and far more dusty sources. And another point to be made from this comparison, as you remember, green peas are with the green color here, is that many of these green pea sources fall within the wedges that are used to identify AGN sources. So indeed, they do mimic AGN galaxies with respect to their infrared light. But this is not the case about blueberries, which are even redder compared to green peas. Moving on to even lower energies. So here I'm just showing quickly the comparison of the blueberry sources regarding the radio emission. So here we see in all these recent studies from Abhijit Burkar, Omkar Beitor, more previous studies for dwarf galaxies, that in all cases, when we examine the radioluminosity of blueberry or green pea or even dwarf galaxies with low metallicities, with respect to their star formation rates, they're underluminous. So this is in low far 3 gigahertz or even 21 centimeter emission. Why is that? We argue that this is possibly due to their not that well-formed magnetic fields or their low gravitational fields that may allow their relativistic electrons to escape more easier compared to more massive sources. Now I will move to high energies with respect to multi-wavelength comparisons. So I will skip this plot in the interest of time where we examine green peas. And since Antara this morning gave us a very good review about X-ray emission, I will skip the explanations and go directly to this plot that shows the normalized X-ray luminosity as a function over star formation rate as a function of metallicity. We've seen that these relations describe the average population of X-ray binary emission in star-forming galaxies. So we have a small sample of blueberries that we've managed to take some XMM Newton observations. So this analysis showed that the majority of those sources are underluminous in X-rays. This is just one source. This is overluminous, but this is one source. This one source is probably an AGN galaxy. So the discussion then is why those sources are underluminous in X-rays. And as Antara said this morning, this is probably related to their very young stellar population ages, which may not have allowed enough time for the high mass X-ray binaries to evolve to produce the X-ray emission equivalent to what we expect from more massive and galaxies that can also include older stellar populations. With respect to X-ray emission, I will just quickly mention, because there is a big discussion about also helium-2 emission. So there is a a tight correlation. We found that there is a tight correlation between helium-2 and X-ray emission that holds for more than 7 orders of magnitude and works for both star-forming galaxies and active galactic nuclei. But for our interest in low-metallicity galaxies, I would say that the comparison in this work, the comparison showed that helium-2 emission can help us resolve the large scatter we see, for instance, in low-metallicity star-forming galaxies. And we see a very nice correlation when we take into account helium-2 emission with respect to X-ray emission. And in the last minute, I will jump back to some analysis based on optical and SDSS data, but this is with respect to the environmental properties of those dwarf galaxies. So here, my colleague Maitreyi Gupta did some very nice work and examined the amount of neighbors that are found for some control galaxies, the amount of neighbors within a sphere of 5 megaparsec. Let me finish this sentence. So what we see here is that in all cases, blueberry galaxies or even green pea galaxies, that are not shown here, have the least amount of neighbors within this sphere. So in that sense, this suggests that their high star-forming activity is not driven by any kind of interaction or mergers, but is probably for some other reasons that we can discuss later. So I will leave you with my conclusions, and I would be happy to take any questions. Thank you very much.
Great talk. I missed, my name is, did you say anything about morphologies? I mean, with the name blueberries, I'm assuming they're very compact, but are they?
Well, that's a very good question. So initially, all of the young blueberry samples were all compact and spherical. So in this analysis, as you can see from these images, we see that not all of them are compact and spherical. There are some sources that have like kind of disturbed morphology, and as you can see, some have belong to systems with some less active star-forming activity, but overall their integrated colors fall within the criteria in order to be selected as blueberries. Thanks.
Other questions?
Yes. What's the link with environment? Like, why do blueberries live in low-density environments?
Well, that's a very good question. The interesting to study regarding environments is why we see such high star-forming activity in these sources. So usually we've seen these high activities after results of merger activities or interactions, but that's not the case for those sources. So what drives those sources to become all of a sudden so active? That's an open question, I would say. I would just mention here that in this study we look to find blueberry sources within the Illustris simulations, but we could not, because Illustris could not produce such blue galaxies, at least this respect. And in all the cases when we found sources at this high specific star formation rates, there were all like dwarf cluster galaxies within like members of other more massive galaxies. So we cannot reproduce them now already. That's the outcome.
All right, let's thank our speaker again.
Okay, thank you. Okay, hello everybody. For those who don't know me, I'm Daniel Pauli. I'm a KU11 FWO postdoctoral fellow. And today I want to talk about adding limit-induced mass ejections and the implications for massive star populations. So the adding limit is, I think, today's topic. I want to make friends because I want to talk about luminous blue variables. So just as a reminder, it's a rare evolutionary phase of massive stars. Yeah, so it's also a very short-lived phase. And the luminous blue variables, they are not always blue and they are not always variable, which means that they're really hard to detect. But they are a very important evolutionary phase because they are unpredictable mass loss events really like change the evolution of massive stars. Side fun fact, yeah, so they also call it S Doradus variables, yeah, after the S Doradus region in LMC where plenty of these ABVs are found. So this is a Hertzsprung-Russell diagram from Vink 2007, where a nice collection of the known ABVs is shown. And you can see on the left over here, this is the quiet S Doradus instability strip. And if they are going into outbursts, they are going to cooler temperatures. And then they have like this eruptive mass loss event where they lose the mass. So their outer envelopes, their atmospheres are loosely bound, which means that they're unstable, which causing this outburst. But the physical process causing the outburst or the mass ejections is not very well understood. But what we know is that all of these stars are very close to the Eddington limit. Before we are talking about the Eddington limit, I want to talk a bit about current problems that we're having with our stellar evolution models. So I'm showing here Hertzsprung-Russell diagrams of the LMC on the left and the SMC on the right. You can see the different symbols are observed stars in these galaxies that have been analyzed with spectroscopic analysis. Then I'm showing stellar evolution tracks of single stars with very typical assumptions of mixing, mass loss, and so on, what you can find in the literature. The tracks are color-coded according to the surface hydrogen abundance. So white means initial surface hydrogen abundance, then you have 70 to 30% in red, then you have like hydrogen poor ones as yellow and hydrogen-free stars as green. And in principle, you cannot see it here, but if you have a Dirac type star, it would be colored in blue. In the background, I'm showing synthetic stellar populations, so where you would expect to see stars to be visible, and you can already see that in the Humphrey-Davidson limit in the upper right corner of the Hertzsprung-Russell diagram, we are predicting a lot of stars that we are not observing. And this Humphrey-Davidson limit is an empirical limit, but it is like valid for all the metallicities or the metallicity environments that we have seen so far. Another problem is that we are really having big problems of explaining the apparent single-Wolf Rayet stars at low metallicity, as Thomas already ruled this out. And obviously, one of the possible solutions would be that we incorporate ABV mass eruptions, or at least the effect of them, into our stellar evolution calculations. So hopefully, when we have a proper model to do this, then we can solve many of these issues. So we already had enough slides about the Eddington limit. So it's a basic idea that if you have a star which is accreting mass, at some point the radiation pressure is preventing you from accreting any more mass. This is a very basic principle, but the biggest question is like, what is happening if you reach the Eddington limit inside your star instead of at your surface? And I think this is a very interesting question to ask. So I have a cartoon here, or it's not actually a cartoon, it's actually a 1D stellar evolution model projected in 2 dimensions so that you can see it even a bit better. In the upper right, I'm showing the energy generation rate. So you can see we have a star which is burning hydrogen in its core, so it's now at the 0H main sequence. This is the 40 solar mass star, by the way. And this 40 solar mass star, it has in the lower right, you can see the density structure. It has a high density throughout the star, and when you approach the surface, the density is quickly dropping. In the lower left, we have the logarithm of the Eddington limit. Yeah, so if it's black, we are very far from the Eddington limit, so our star is just born and it's far away from the Eddington limit. Everything is fine. And the upper left, we have the gas pressure. So you see like the gas pressure divided by total pressure is dominating, which means our star is more or less an ideal gas. We can debate about this. It's not really true, but. So what happens if my star is then evolving? Yeah, so this is now at 80% of core hydrogen burning, so close to the TEMS. And you immediately can spot that when we are looking at the Eddington limit, that I now have local layers which are reaching or even exceeding the Eddington limit. As a reminder, this is the 1D stellar atmosphere model. So what is happening in these layers? In these layers, the densities are low, and you have a lot of energy that you want to transport. But convection, because of the low densities, is no longer efficient in transporting this energy. So my 1D model has to transport the energy via radiation. And to do this, I need to lower my opacities. And if I want to lower my opacities, I have to expand. So my model is actually inflating and blowing up artificially in 1D. And then, this is the worst part, at the outer layers, there's a density inversion, so there's a density inversion, which is acting as an inward pressure gradient, which is stable in 1D, but let's be honest, in 3D, this cannot be stable, right? So there's like 3D mixing effects and so on, which can make everything going berserk. Another cool feature is that you can see that if we have this radiation transport happening, is that the gas pressure is now dominating instead of the the radiation pressure is dominating instead of the gas pressure. So which means that we can use this fact to check when the gas pressure to total pressure gradient is dropping to define the non-inflated stellar core and calculate in such way the inflation radius as the radius of my 1D stellar model compared to this non-inflated stellar core model. If I do that, I can plot again the populations of the SMC and the LMC in the Hertzsprung-Russell diagram. Now I'm showing still stellar evolution models without accounting for LBV mass loss. But you can see in the background, I color-coded the inflation levels of my stellar models. And you can see that we have constant inflation levels, which are parallel to the Humphrey-Davidson limit, which I find really suspicious. So there seems to be a link between the stars that are inflating and getting unstable envelopes and undergoing mass ejections and the Humphrey-Davidson limit. This is, by the way, also the region where the LBV instability strip is located. Okay, so we can use this one as a criterion, an empirical calibrated criterion, when to increase the mass loss rate to approximate the effect of mass ejections. So I'm not modeling the injections themselves, but only the effect of the mass which is lost. Okay, this is core hydrogen burning stars. What about helium stars? Yeah, they can also inflate, but they might inflate in a different way, or the inflation might be less stable. So we can also look at the Wolf-Rayet populations. So I've calculated helium star models, yeah, so like helium 0H main sequence models, and calculated the point at which they are inflating. And this is something which is really interesting. Thomas was talking about the lower luminosity limit. But actually, if you now look, there seems to also be an upper luminosity limit of how luminous a Wolf or a classical Wolf-Rayet can be in a stellar population. And this is about 10% inflation. So I'm using this as a second criterion for stars with hydrogen-free stellar atmospheres to increase the mass loss rate and remove all the layers that are inflating beyond this point. Okay, so how does this compare to my stellar population? I decided to talk about the LMC only because I have binary models for it. Yeah, I know it's a higher metallicity. You can ask me about the SMC, but I will not have time for this. So per design, there are no stars in the Humphrey-Davidson limit because my stars are now turning around. If we look at the Wolf-Rayet population, so you can split them hydrogen-rich, hydrogen-poor, hydrogen-free, and the WCWOs, for me, it's the same. Yeah, it's like carbon-enriched surfaces, right? So you can see the hydrogen-rich population matches a number and also the luminosity distribution. The hydrogen-poor only matches the number, but is not fitting the luminosity distribution very well. The hydrogen-free is also quite decent. For the WCWO, I'm missing many of these very bright WCWO type stars, but there's a small disclaimer. So you can see that there are two colors in this luminosity distribution. The dark diamonds, the dark blue diamonds, these are luminosities obtained by doing a proper SED fitting with stellar atmosphere models. The light blue ones are luminosity calculated using a bolometric correction and the V magnitude. So please don't trust them. Yeah. So if this is a binary or the correction is not really working properly, the luminosities are highly overestimated. Okay, another feature is we can observe the faintest Wolf-Rayet star. Yeah, this is really nice in the galaxies. This works also, by the way, in the SMC, which is really awesome. We can also look at other populations. Yeah, let's look at the cool side of the Hertzsprung-Russell diagram. There are the red supergiants. Yeah, so we can get the red supergiant population very well. This is because of my choice of the red supergiant wind. But it also helps a lot to have then after the red supergiant phase a little LBV outburst. So we can see there are little LBVs also observed in this regime where I'm also triggering my LBV eruptions. And this helps to get rid of the remaining hydrogen-rich envelope and to create the missing Wolf-Rayet stars, the apparent single ones. The yellow and blue supergiants I'm not getting very well, but as Asira demonstrated yesterday, these are most likely coming from stellar mergers, so we don't have to worry about them too much. Okay, as we also have heard, like most stars are formed in binary systems, so trying to explain the world with single star models is something like 1970-ish. Let's do some binary models, yeah. But calculating a large grid of binary evolution models is really expensive, yeah, not only money-wise, but also time-intensive. So I can combine it still with older populations. Yeah, so I have like a paper from 2020 where we calculated binary evolution models at the LMC up to 90 solar masses. Obviously, I didn't have LBVs accounted in there, so I had to merge a little bit models. So if I have an ABV phase, my maximum radius is limited, but you can still glue everything together. And we have to do the crude approximation that above 90 solar masses, ABVs are dominating, but the maximum radius my stars are having is something like 30 to 50 solar radii. So the parameter space where in the binary they can interact is not really large. And another crude approximation is if my stars are merging, I assume that they can be represented by a single star model. As Athira has demonstrated, this is not a really good approach. You should do it properly, like she is doing, but this is the best I could do to get the numbers of the stars, at least in the direction. So this is the Hertzsprung-Russell diagram and the luminosity distributions of the binary population. Again, per design, I'm not getting any stars in the Humphrey-Davidson limit. I'm getting more now of the strip stars or the intermediate strip stars below the Wolf-Rayet population. And the luminosity distributions of my Wolf-Rayet populations have also changed. So now we are really good explaining not only the number of the Wolf-Rayet population, but also the luminosity distributions by themselves. And binarity becomes really important for like 28 to 40 solar mass stars, and they are feeding into the lower luminosity Wolf-Rayet population quite significantly and adding up there the luminosity distribution. Also for the WCWO type star, we are getting a bit more, so in the numbers matching the luminosity distribution has to be handled with care. And there's one really cool thing is, I can also calculate my binary fraction, right? And Thomas already mentioned this. So most Wolf-Rayet populations are expected to have 40 to 50% binary fractions. And in the LMC, there's only one measurement, which is not bias corrected, which is 30%. And my prediction gives 43%, which is very well in agreement with our expectations. And I think it's solving one of the biggest issues we had so far. I will not talk about the red supergiants. They are still matching if you put the mergers into the yellow and blue supergiants. And my time is up now. So thank you.
Questions?
That was fantastic and very convincing. I can ask you afterwards several questions, but I will focus on one, which is I'm not sure I understand why the red supergiants below the Humphreys-Davidson, since you were calibrating your model based on the Humphreys-Davidson, how come they also suffer suddenly from eruptions in your model?
Yeah. Very good question. So I'm using relatively strong red supergiant masters rates. So I'm assuming that they are driven by turbulence. So they have no metallicity dependence, which means that you get rid of your hydrogen-rich envelope, which is also convective, quite efficiently only via the red supergiant wind. And what is happening then, if you get rid of the hydrogen-rich envelope, is you're exposing the interior of your star, where you have a steep drop in the gradient, yeah, in the pressure to total gas pressure to total pressure gradient, and then you trigger the criterion for inflation after you get rid of the convective envelope. And this is really nice. And I mean, these stars are, how do you say, hydrodynamic unstable anyways, so it is in support with other models.
Great talk. But my question is regarding how you get to the LBB stage in the first place. So it wasn't entirely clear to me whether a regular 25 plus solar mass star will always hit LBB, or whether you need, a smaller core for a larger envelope to get in that stage. And if that were the case, if you have super early mass transfer in your evolution, and you have these like small cores for great masses, are you more likely to become LBB-like?
I'm not sure about the core sizes. I've not thought about this. So, but essentially what's driving is your L over M ratio. So if you strip your star via wind, mass transfer, whatever, you get closer to the Edding limit also locally. So every time you strip or remove mass, you get closer to this, which is then fueling the inflation. And the other effect is, of course, the opacities that you have. Yeah, so if you have decent opacities, yeah, the kappa, then you inflate more strongly. And you can also see this in the, I cannot zoom back, but in the inflation levels where you could see it, there's a weak metallicity dependence if you go from the LMC to SMC. And we are currently calculating also models at extremely low metallicity, like 10 to minus 5 of solar metallicity. And there, of course, you're not inflating on the main sequence, but beyond that, you still have inflation because you have the hydrogen opacity bump, which is then powering the inflation. And then you still have ABV mass loss rates going back to the blue and hot temperatures. Okay.
Yeah. All right, let's thank our speaker again.
Hi, I'm Archana, and I'm a postdoc at UT Austin, and today I'll be talking about some of my work that I've been working on to try and understand the hard ionizing continuum in some of these low metallicity extreme emission line galaxies. So we've already saw a lot about extreme emission line galaxies, and Daniel gave a really nice review talk on Monday. But just to quickly bring you all up to speed, extreme emission line galaxies are characterized by their extreme emission lines, but they're also very compact, have low metallicities, and one reason why it's very interesting to study about them is because they are expected to have conditions very similar to the conditions of the early universe, and we do have a number of them in our local universe. So this allows us to really perform these in-depth studies of these galaxies and allowing us to study the conditions and the ionizing sources that were likely present in the early universe. So some of these extreme emission line galaxies were found to have very high ionization lines. So again, this was also talked about a lot over the past couple of days. Some of these, so these are two galaxies from the classy sample. So these have low metallicities, and you can see these all have a bunch of very high ionization lines, including helium-2. And we've seen, again, a lot of this that these cannot be explained by currently available stellar population models. So this is, again, just your stellar SEDs from your stellar population models. And then you can see as the helium ionizing front and the neon-5 ionizing front, the number of available photons drops down significantly. And this is one reason why it's possible that this could not explain, just using stellar population models cannot explain your high ionization lines. So this is shown very nicely by Grace's Olivier's work, where they found that you can kind of use your stellar population models to explain your low ionization lines, but then when you look at your higher ionization lines, which require higher ionization potentials to form, these models don't do a good job. A lot of work has also been done to try and understand what are other alternatives that can help explain this excess helium-2 emission and other higher ionization lines. Again, a lot of this was also covered. So Wolf-Rayet stars, and there's a lot of caveats associated with it, but we don't see any obvious features associated with Wolf-Rayet stars in some of these extreme emission line galaxies. Again, Grace's work also saw that you could add an additional black body, and that can possibly help explain these high ionization lines. More traditional physical explain methods, again, a lot of it was covered today. X-ray binaries, high mass X-ray binaries, but all of these have not been very successful in helping explain these excess helium-2 emission. And again, a lot of work has been talked about again in this conference, some of them with varying levels of success in helping explain these extreme emission lines. Another alternate source also covered today are ultraluminous X-ray sources. Antra did a really nice job of covering this. So these are your more extreme cases of your high mass X-ray binaries, and these are formed when you have super Eddington accretion onto a compact object like a stellar mass black hole or a neutron star. And they can, in principle, provide your hard tail to produce your helium-2 emission, especially probably at lower metallicities. But again, this was also covered that they are very strongly tied to the ages of the underlying stellar population. There's this time delay for which they can start to affect or contribute significantly to the tail, and this is typically set at about 5 million years. A lot of these extreme emission line galaxies often have smaller burst ages, so they don't really have the typical ages you would expect that could contribute significantly to your to a ULX providing this hard tail. So for most of the talk, I'll be focusing on these two galaxies that I introduced briefly earlier, J1044 and 1418 from the classy sample. So J1418, for example, so these are stellar population obtained by fitting the UV stellar continuum from Parker et al. And then you can kind of get this distribution of how much each age contributes based on your light fraction and mass fraction. And for your 1418, for example, you can see they're very small burst ages. You don't really have any significant contribution for ages over 5 million years. So you don't really expect a significant contribution from ULXs here. 1044, on the other hand, could have some contribution. So we wanted to explore and see whether the ULXs can help explain the high ionization lines present in 1044. So to do that, we constructed these stellar plus ULX SEDs, again following from Kristen Garofoli's work, which very nicely ties these X-ray populations to your stellar population. So when you kind of look at your different stellar ages that contribute to your stellar population, so in this, for example, you have your 1 million years, you don't really get this hard tail because you don't expect ULXs to form from such a young population. And then as you go to your older ages, that's when you start getting these this contribution. So we constructed these stellar plus ULX SEDs. So we did a linear combination of the different ages that actually comprise of the stellar population to get this combined stellar plus ULX SED. And we ran our photoionization modeling to see if this can explain the excess helium-2 emission. And we find out it doesn't really go a good job, especially with helium-2. So it does a good job in explaining your lower ionization and even higher ionization lines. But then when you do this kind of linear combination tied to the ages that are present in a stellar population, it doesn't really help explain the helium-2. So helium-2 is still being underproduced by these models, and we cannot really we see that when you kind of account for these ages, ULXs do not do a good job in explaining this excess helium-2 emission. Another source that could also provide your tail are your AGNs. So AGNs in dwarf galaxies have always been, can you even expect to find AGNs in these small galaxies? But now with more and more bigger telescopes and larger surveys, this really has been kind of pushing the boundaries over the past decade or so. So now we are finding more and more hints of AGN in smaller and smaller galaxies. So this is a plot of type 2 AGNs, so your more, I guess, typical AGNs that are found from the DESI sample, and you can see it's going down to smaller and smaller stellar masses and at higher and higher redshift. So just to give you a comparison of expected black hole masses, so this is, you're really probing this intermediate mass black range, and you're going down to smaller and smaller stellar masses. So this is, again, like I said, this is your typical type 2 AGN, but there's also a lot of work that's been done by a lot of people trying to find different ways in which you can actually find AGN in these smaller and smaller galaxies. So there's been variability studies, radios, X-rays, high emission lines, and so on, because the challenge is it's really hard to distinguish between AGN and star formation when you go to low and lower mass galaxies. So we've seen a lot about this. Your traditional diagnostic diagrams, they're all calibrated when your AGN is contributing significantly to the ionization source. But when you go to smaller and smaller masses, that doesn't really have to be the case. You can have your AGN and star formation both in tandem, and it's getting really hard to distinguish these in low mass galaxies, and we need to come up with better methods to do that. But again, so in principle, AGNs can provide the hardtail to produce your higher ionization lines. A lot of people have explored these works, and then the result has always been very inconsistent. So even your AGN can explain your higher ionization lines, but then it also boosts your lower ionization lines, or it overpredicts your helium-2 emission. So there hasn't been a very self-consistent way in which AGNs have been modeled and thought as possible contributors to this excess emission in these small galaxies. So what we explore is now constructing stellar plus AGN SED. So again, the UV ionizing spectrum of these galaxies are very well studied. So we do know there's a significant stellar population that's going to be contributing to your ionizing source. And the challenge is to see whether you can have an additional source that is used in combination with these stellar SEDs, and if that can help explain your AGN contribution. So to do that, we use AGN templates, AGN SED templates that are better suited for these lower masses that of the black holes expected in these smaller galaxies. And then we scale it based on this AGN component, which we define as the fraction of the total ionizing photons contributed by the AGN. So your AGN is contributing some fraction of the total ionizing photons, and we add this SED based on that. So here this, so we go from 1% and so on, and we add on and get these combination AGN stellar plus AGN SEDs, and then now we run our photonization models with this. One thing we do see is that your AGN, how they affect your helium ionizing photons. So this is a factor, this is a plot showing this is your helium-2 ionizing photons over your hydrogen ionizing photons. And this is the observed value for these galaxies from Daniel Berg's work. And you can see the stellar-only models grossly underpredict the helium-2 ionizing photons. But then when you start adding your black holes or your AGN, you can see they very quickly kind of contribute to this hard tail, and they can reach the values that are predicted. So you don't really need a significant AGN source. And then you can see that they quickly take over at very small AGN fractions, and you're already able to have sufficient photons to reproduce the expected helium-2 emission. For comparison, this is the stellar and ULX SED, so this is the exact value. So we see that you need to be boosted by about 70 times to reach these values, and they don't do a good job. So the AGN fraction was kind of limited to be less than 5%. So again, now we wanted to see if this added AGN fraction can help explain the observed emission lines. So these are the higher ionization lines, like helium-2, neon-5, oxygen-4. And you can see that at very small AGN fractions, you are able to kind of reproduce these emission lines in these galaxies. And then we find that you just need about a 2% AGN fraction, and this is able to self-consistently help explain your low ionization as well as high ionization and your very high ionization. So because the AGN contribution is very small, you don't really see a significant difference at your low ionization species. It really is at these very high ionization lines you can see this very distinct difference. So when you have no AGN fractions, it's very low, and even at a 5% AGN fraction, you're already overproducing your helium. So there's this very small contribution from your AGN that could possibly help explain this excess helium-2 emission. So that kind of brings back to our big challenge. A lot of these AGNs are hidden in these small galaxies. There seems to be some evidence. There's a broad component in some of these galaxies which occupy or contribute about 1 to 3% of the Mama fluxes, and we do kind of see these in a lot of these small dwarf galaxies. And a lot of simulations also predict that it's very hard to distinguish these, and you can kind of see when agents only contributing such a small fraction, it just becomes challenging to find them. So again, there's still a lot of work that's coming. So mid-infrared diagnostics have been predicted to do a better job, especially at smaller AGN fractions. So we do have MIDI data for some of these galaxies, and Kaylee will be talking a little bit about it. So we'll be kind of making use of that to try and see if we can tease out this AGN fraction better, or the AGN indicator better. But we do find that stars are likely still your more prominent source of ionizing photons, but you can have some contribution from the AGN, and that can help dominate the high energy photon production. Of course, this leads a lot of questions on how these black holes are formed, seeded, and how they co-evolve with the galaxy and so on. So I am out of time, so I will quickly put up my conclusions. I'm happy to take any questions.
I'm invoking my privilege as chair. So JSON44 and KCWI maps indicates extended supersonic flows across the whole face of the thing. It shows filaments and ejecta and things like that. Flows at hundreds of kilometers per second are supersonic, which means there are shocks. So have you considered the fact that shocks could be, especially if you only need a few % of ionizing photons to come from a non-stellar source? Is it entirely plausible that shocks could do this instead of an AGN, and is that something that you've looked into?
Yeah, that's a really good point. And yes, shocks in principle can also produce these emissions. I think the issue with shocks is that it's kind of I think based on work that have been done, it's not able to like self-consistently explain it. So it can do a good job, yes, maybe of explaining the helium-2 emission, but can it also consistently explain your lower ionization lines? I think based on previous work, it was not found to be that self-consistent, but with better shock models, I think it's possible to explore that. So yes, in cases where you do have these kind of outburst signatures, I guess it becomes a little more muddy, but like 1418 and some of these other galaxies, you don't really have that. So there, I think the question is what is covering the emission, and it could be a hidden AGN like this. Yeah.
Thanks for the nice talk. For the AGN to contribute, 1 to 3% like you found here, of the, I'll see, I'm not sure if that's like volumetric fraction or what. Do you have an idea of what fraction of Eddington that AGN would need to be accreting at the mass ranges?
Yeah, so again, this is based on in your SED models, you can put in like an accretion rate. So these are all at like 0.1%, so 10% accretion, mass accretion. So this is just like how the models are calibrated. You could go lower. So when you go to like lower limits, like I did do for like 5% accretion rates, then your AGN fraction actually increases. But then the issue is, again, I guess I haven't tested very well like how low you can push it, but at least based on what you're seeing, that if you have a less accreting black hole, it does seem to kind of boost the AGN fraction slightly more. So it's a fraction of like ionizing photons that are contributing, coming from the AGN. So,
but I guess there is a limit that if there was a efficiently accreting black hole, it would contribute too much.
Yes, yeah. So I think if you go to like higher accretion rates or like more effectively accreting this thing, yeah. So then I guess your AGN fractions would just get smaller. But yeah, we still don't have a good handle. I mean, if it's efficiently accreting, you should get more obvious signatures, right, which aren't. So I guess the idea is
which I guess we don't see in any of these things.
Yes, yeah. So maybe they aren't really efficiently accreting. So it just makes it harder to like see these in observations.
So in this mixed accretion rate scenario, is there much hope for eventually teasing out that black hole mass, or is it just too difficult?
Yeah, so at least as of right now, it's been very difficult to kind of separate out like the black hole masses, because at these kind of fractions, they are very similar, like whatever range of masses you do. So the goal is to maybe kind of use, so like the UV and all the traditional UV optical diagnostics, they haven't been helpful, but there is some hope. There's some work that showed that the mid-infrared can do a better job, so maybe we can kind of use the mid-infrared. I'm not sure if that will kind of help us separate out the black hole mass, maybe at least help us confirm the AGN fraction. But yes, as of right now, it is, I guess, harder. We're just going off like seeding models and expected relations. But yeah, hopefully, I guess there's still lots to explore and see if we can kind of get a better handle on the black hole mass.
Getting upper limits though from your cube.
Yes, yeah, that's true. Yeah, upper limits at least. Yeah.
Sorry, you may have said it and I missed it, but so do you see neon 5?
Yes.
And you can reproduce the emission with this 1 to 2%.
Yes, yeah, there is neon 5. It's very faint, and then we do have better neon 5 from the mid-infrared, so that I will, this is still like there. But yeah, it's still very small, but this 1% can reproduce it.
Harley? Thanks for the nice talk. I had a similar question to Ryan and like Christy. So if like you use like Kubota and Dunn gives you an absolute luminosity, right, not a fraction. So I was wondering if you tried to use like a single epoch virial estimator based on the broad line, which is like admittedly dubious, but then everybody at high-redshift uses it. So it's okay. Like try to see if it matches kind of the luminosities that are coming out of Kubota and Dunn SEDs.
I haven't looked at the SEDs, like the luminosity from the SEDs, but it's a good point. So I will, yeah.
Masses are the same.
Yeah, we did use the same masses, for these, but I didn't explicitly check if the luminosity is reproduced by the SEDs, but that's a good point. I'll check and see if it kind of agrees. Yeah, thank you.
All right, I appreciate that there are a lot of questions and enthusiasm about this. So we're gonna move that over to the break and the Slack channel. Thanks, thank our speaker again.
Thank you, wonderful job.
All right, I'd like to start by thanking the organizers for giving me the opportunity to present to you about this very exciting galaxy, a Lyman continuum leaker close to the epoch of reionization. I will say that unfortunately I can't show these lovely high resolution spectra that we've seen throughout this week with lots of emission lines. We will talk about the stellar population of this galaxy, but it'll be more through inference than through direct detection. So I'll start by introducing reionization, although that needs no introduction in this room, I think. I found it interesting that this week it seems to me that it's this diagram of the history of the universe that we've settled on as our favorite. I saw a bunch of them during my thesis, but I do like the way that this one shows the first galaxies creating these bubbles in the neutral IgM. Those bubbles slowly percolate until the IgM is fully ionized around redshift 5 to 6. And as we know, a lot of outstanding questions remain, particularly about how this process happened and which sources contributed the most. Also, as we know, the principal actor in this process was Lyman continuum emission. Lyman continuum photons, energetic photons capable of ionizing atoms of hydrogen, emitted bluewards of 912 angstroms. And I'm going to talk in particular about Lyman continuum emission at high redshift. So at high redshift, we have the issue that these photons are absorbed by the neutral IgM along the line of sight, absorbed and scattered. So we study this ionizing emission at low redshift, where we have these wonderful detailed studies and we can resolve a lot of things. However, we do need to understand this emission as close to the epoch of reionization as possible, because we undergo 8 to 10 gigayears of evolution, of galaxy evolution in this time, most of the history of the universe. And a lot of things change during this time. The UV background changes, the star formation efficiency changes, and as we've heard this week, the metallicity changes, the ISM gas density changes. So I hope I don't need to convince anyone that it's important to validate everything that we understand at low Z as close to the epoch of reionization as possible. So the state of that effort at the moment looks like this. We have samples of tens of Lyman continuum emitters at low redshift, up to maybe about 100, so we can build up proper statistics about characterizing this emission, and also establishing traces that we will be able to use at higher redshift. Then at around redshift 3 to 3.5, where we're now within 1 to 2 gigayears of the end of the epoch of reionization, we have some tens of Lyman continuum emitters plus some stacking analyses. With the current redshift record, let's say ion 3 at redshift about 4. I say current. This is the galaxy that I'll be talking about, a Lyman continuum leaker at a redshift of 4.442. It's detected in Hubble's F435 filter in the Mu's extremely deep field, which gives its name to the galaxy. And it has its redshift confirmed by a nice, strong, asymmetric Lyman alpha line in the Mu's data. So there's lots of things that I could tell you about this galaxy. Unfortunately, I don't have time to go through all of them in this talk, so I'll focus on the stellar population. But very quickly to show you the detection here in F435 of the Lyman continuum photons, and this is the Mu's spectrum, so 140 hours of Mu's exposure time in this field. We don't see any other lines in the Mu's spectrum, but we do see this nice asymmetric Lyman alpha line. So the way that I'm going to segue into talking about the stellar population of this galaxy is through an analysis of its escape fraction. So the escape fraction is not something that we observe. It's a product of these three things, one of which is observed. So this is the ionizing flux fraction. So simply the flux in the filter that sees the ionizing radiation over the flux that sees the rest frame UV. It has nothing to do with models. That's just an observed quantity. However, we then need to combine that with this luminosity ratio. So the ratio of UV photons produced to Lyman continuum photons produced. You can think about that for every UV photon, how many ionizing photons are produced. Now, this is not observed. This depends on models, and I'll talk a lot more about the modeling that we've done in a moment. And then finally, at redshift 4.5, it's of course crucial to take into account the absorption by the IgM. That's encoded in this TIgM parameter, the transmission of the IgM. Again, this is not an observed quantity. This is a quantity that we have to derive through modeling. And we can consider that as what fraction of the intrinsic flux, ionizing flux emitted in situ by the galaxy gets through to be observed by us. So this is the distribution of 10,000 mock IgM sightlines that we modeled with this parameter here. And maybe on the next slide, yes. So we know that this sightline must be above average transmission, or there's no chance that we would observe Lyman continuum photons. So in our remaining analysis, we consider what we say is a 3 sigma unlikely sightline with this high, relatively high IgM transmission of 18%. Now the issue is we actually observe a flux fraction of 18%. But of course, this intrinsic Lyman continuum escape cannot be more than 100%. That's unphysical. So what does that leave this luminosity ratio as being? So it leaves it around 1. So that's, we can think about that as 1 ionizing photon produced per UV photon, which is a huge amount and absolutely not what we expect in normal galaxies or even star-forming galaxies. So when we discovered this, we then obviously thought, what kind of population can create this? Now I'm going to preface the next section of my talk by saying that over the course of this week, it's become, or I have much better appreciation that actually we don't have a great handle on what kind of populations can create these amount of ionizing photons. And I'm certainly intrigued to hear what people in the room think about this. But so in this effort, we turned to models of stellar populations appropriate for Lyman continuum production. So in particular, we considered B-pass populations, which include binary stars, and pi starburst 99, which includes the effects of stellar rotation and very massive stars. We fit the SED a couple of different ways. And then we also, because during our SED fitting, all of our runs showed that there was a very recent, very vigorous burst of star formation in this galaxy. We then turned to B-pass and starburst 99 and looked at what that recent burst could have looked like in terms of this ratio, this luminosity ratio that I've been talking about, which is something intrinsic to the stellar population, and its evolution with time after a burst. So if we assume this IgM absorption transmission of 18%, which, as I say, is already a 3 sigma unlikely sightline, this is our constraint on what this ratio must be in order to have a physical Lyman continuum escape. So we can see, firstly, that we're talking about very young stellar populations and likely very metal poor stellar populations. Even if we consider the single most transmissive sightline in our modeling, the 1 in 10,000 sightline, which is about 4 sigma unlikely sightline, 26% transmission, we're still, look, we can go out almost to 10 mega-years, but then we really are considering the most extremely metal poor stellar populations capable of producing this number of ionizing photons. And then after that, given that we see those things, what can we assume, or what can we infer about the process of reionization, which, if you remember, is the original question, what galaxies contributed most of this process? So based on this galaxy, MXCFC 4.4, we would suggest that bursty star formation creates scenarios, firstly producing many ionizing photons, and then facilitating escape from the host galaxies. So when I prepared this talk, I was going to say through supernova feedback and through radiation feedback, but again, I'm now going to generalize that based on what I've heard this week to just feedback. And as we also know and have heard this week, JWST has observed an increase in the stochasticity or burstiness of star formation during the epoch of reionization. So what this result suggests is that if these bursty galaxies also undergo periodic episodes of very high Lyman continuum, both production and escape, that these might really have an enhanced contribution to reionization. I see I have a little bit more time, so I'll go through my conclusions. We report the most distant Lyman continuum leaker at a redshift of almost 4.5, which, actually I should have mentioned this earlier, is just 250 megayears after the end of the epoch of reionization. And no matter which way you slice it, an extreme stellar population is necessary to explain the observed Lyman continuum flux that we see. And the most likely explanation based on our stellar modeling is a recent burst of extremely metal-poor massive stars, which both produce the amount of ionizing photons that we need and clear the ISM, enabling them to escape. And again, this suggests that bursty star formation may have played a key role in allowing the requisite number of Lyman continuum photons to escape during the epoch of reionization. Thanks very much.
Questions? Yes.
Hi. Given the previous seminar that we have you considered any contribution from AGN?
So we did think about AGN when we found this galaxy. The issue really being is that it's hard to rule it out because we don't have JWST spectroscopy. We have, one thing I would say is that the Lyman alpha line is actually not that strong. So it's not a booming 1,000 angstrom equivalent width Lyman alpha line. So that at least suggests that it's not an AGN, but no, we can't. And it's not a pointer source, so it's not a quasar. But yeah, we don't have the JWST data necessary to really rule out the fact that there isn't any AGN contribution.
Would be a mix, right? Contribution.
Sure. But that, I think, well, we know that that's very difficult to establish even if we did have all the data necessary.
Just looking at the image, you see that the Lyman continuum is on one side of the galaxy, yet you are doing this integrated. So do you think this will matter when you estimate the Lyman continuum escape? So if you use the PSF, it's like you have two PSF overlapping the 606, but the Lyman continuum is coming only from one region.
It's true that the Lyman continuum, yes, is certainly smaller than the full galaxy. What I expect to be happening here is that it is emitted only from some small parts of the galaxy where we have this extreme population that I was talking about. Because actually, when we do full SED fitting, we do have a little bit of dust in this galaxy, at least suggested by the SED fitting, and there is an older population as well. You can see it's quite bright in the JWST near-cam filters. So that's what I expect to be happening here, that we have this small region producing Lyman continuum flux, and then another population also existing in the galaxy. But yeah, everything we've done has been on an integrated basis, yes.
Yes, so is the Lyman alpha offset compared to
Spectrally or spatially?
spatially?
So I have quite some Lyman alpha analysis in the paper, which I haven't spoken about in this talk. But so the short answer is no. It is co-spatial with UV. The more complicated answer is that because we are only at Muse resolution for the Lyman alpha, I mean the great advantage of Muse is that you get spatial and spectral information, but you have a large pixel size and a large PSF. So actually, in the center of this object, it's hard to put the centroids together. So yeah, we don't really know, but it's at least not massively offset.
Have you considered alternative redshift solutions for this object? Like if the line is oxygen 2, then you might not see any other lines, and then the Lyman continuum is actually just not Lyman continuum.
That's oxygen 2 in Muse. So we spent months verifying the redshift of this galaxy.
But you have carbon 3. Okay.
No. So sorry. These apologies. This isn't the spectrum of this galaxy. Okay. This is a spectrum of other galaxies with interloper lines at the same wavelength in Muse to show that if it was carbon 3, it would be resolved. If it was oxygen 2, it would be resolved. Okay. And similarly, we rule out the other O2, H alpha, and O3. yeah, in essence, yes, we spent a long time checking that it was definitely the right redshift. I'm happy to go into more detail about any of these.
Ryan, very quickly?
Yeah, I did the opposite question of the spectral profile of Lyman alpha. Again, I know you don't have another redshift like to look for offsets of that, but can you say anything about like whether the radiative transfer is suggestive of like a more porous medium that you might expect?
So Lyman alpha does have a couple of interesting. Yeah. So it does have a couple of interesting Lyman alpha properties which we might not expect. For example, it has actually a very low equivalent width, although that is something we do expect if it's really high escape fraction. So not necessarily that surprising. And spatially, we look at the halo fraction, which is this tracer that Alberto established last year with the Lacoste sample. We looked at that for the first time at high redshift, and we get not great agreement, but it's one galaxy, and at least its halo fraction is low. That's spatial.
I'm thinking mostly like width and shape.
Yeah. So in terms of the spectral Lyman alpha properties, it is quite a narrow line. So that that roughly agrees with the interpretation of high Lyman continuum escape. And as you said, we don't have the systemic redshift to really nail down whether this is on the systemic redshift, which would be the biggest. That's the best indicator of whether it's got high escape fraction or not.
Great. Thank our speaker again.
All right, and then we have a few flash talks. These are all virtual, so give me a quick second. We'll get everyone's slides up. But do we have the virtual participants? You? Right here? Okay. All right. Great. So just to briefly recap for the virtual people, I'm going to show your slide, and you will get the 2-minute counter, and then we'll switch on to the next person. But I'm going to be locally managing the slides. Okay.
Great. Can you all hear me?
Yes.
Yeah. Perfect. All right. Hello, everyone. My name's Kieran Fury. Hope you're all doing well. I'm a PhD student at Armagh Observatory. Today I'll talk about a project I did with many great people, the wind properties of O-type stars at sub-SMC metallicity. So what we did is we gathered a sample of 11 O stars across 5 dwarf galaxies in the local group with metallicities lower than the SMC. We analyzed their optical and UV spectra and fit stellar atmosphere models to their spectra to get stellar and wind parameters. And our main result is as follows. It's shown in the plot. So what we did is we compared our wind parameters to a recently derived empirical relation of the wind momentum as a function of luminosity and metallicity. So this is BAX 24. And we extrapolated it down to sub-SMC metallicity, which is what you see in the yellow and purple dotted lines. And we find, albeit with a bit of scatter, qualitative agreement with these extrapolations. Now, what does this imply? This has been the topic of discussion all week. So if you're canonical O stars at 10 to the 5 solar luminosities, at low metallicity, they probably lose negligible mass compared to their high metallicity counterparts, suggesting mass loss has a negligible effect on their mass evolution, but also chemical and mechanical feedback. But perhaps more interestingly, when you look to high luminosities towards very massive stars, and this empirical relation suggests a weak metallicity dependence due to very massive stars' natural proximity to the Eddington limit. So it's very likely these very massive stars in the early universe lost a lot of mass and drove strong, fast winds. But this is a small sample. This is a fit to 6 stars, and so we should all stay tuned for what tempos will reveal on this question. So thank you very much.
Hello, hi, can you all hear me?
Yeah.
Yeah? Okay. So, hi everyone, my name is Julia Camões. I'm a PhD candidate at the ARMA Observatory and Planetarium, and today I'm going to talk a little bit about the project that I'm currently working on. So, the initial idea for this project was to derive the physical and wind parameters for a sample of stars from the LMC. Up to this point, we're on a count of 26 stars. And this process was made basically from a two-step approach. So the first one would be to compare our observed data to a grid of 300 models that span from different values of temperature and log G. And then after a chi-square analysis, we get our best model, and then we further model with CMF-Gen to fit the specificities of the observations. So this is what you're seeing here as an example. I have two objects. So a O4 supergiant here in the lower left corner of this slide. And we have an O5 dwarf, which would be the lower luminosity end, and the O4 and the higher luminosity end. But what I would like to talk more about this today is some things that we are currently finding from this data. So we're basically mostly done with the fitting, with the model fitting. And now what we see here in this plot on the right is on the x-axis a theoretical mass loss determination from Vink 2001, and in the y-axis the derived mass loss rates from our work. And what we see here is that in the high luminosity end, we have a good agreement between theory and observations. However, when we look at a lower luminosity end, we see that there's an offset of around 1 dex, suggesting that the derived mass loss rates are much lower than the ones that we would predict by theory, suggesting the possibly a Weakman problem for our sample here. So this is what we're currently investigating. So if you have any questions, any suggestions, or you're interested in a topic, please don't hesitate to talk to me. And thank you.
Hi, can you hear me? So, hi everyone, my name is Haralambos Daoutis and I'm a postdoc at the University of Geneva. Today I will talk you about a very interesting project that I have been involved the past few months. This project focuses on the study of the metal poor galaxies, of course, showing extreme emission lines, characteristic of galaxies hosting hard ionization fields. In particular, the goal of this project is to answer the following questions. What is the nature and properties of the X-ray sources found in these galaxies? The second is what are the mechanisms producing these observed high ionization lines? Also, are these galaxies responsible for the ionization of the early universe? And finally, we aim to provide a multi-wavelength observations, a public sample for these galaxies from X-rays to radio. On the right, we see the position of these galaxies in two plots. The one is the main sequence, and we see that these arrow galaxies show high specific star formation rates, and most of them have metallicities below 10% of solar, and all of them show helium-2 emission around 1 to 5%. Helium-46 and 86. Some preliminary results show that we detect neon 5 in the infrared in the 14 microns for about 40% of our metal poor galaxies. And another very interesting result that we are trying to investigate right now is modeling of these galaxies so that the neon 5 can be explained and also the lower ionization lines can be self-consistently explained by contribution of a small fraction of intermediate black hole, and not only from young SSPs. And shocks are a bit weird to explain all the observations from infrared to the optical. So this is what I had to present to you today. Thanks.
Okay, so we're going to have our coffee break now. Don't forget, there's also poster session time out in the cafe area. And we're going to be reconvening at 3:45.